Hello and welcome to episode 30 of George's Random Astronomical Object. Every episode, I run a random number generator to select random astronomical coordinates in the sky, and I then search for an astronomical object near those coordinates and talk about what makes that object so interesting to astronomers. So let's run the random number generator. And the random number generator has dented itself while trying to generate the coordinates for this episode. The coordinates are 11 hours, 18 minutes, 16.3 seconds right ascension, and negative 32 degrees, 48 minutes, 45 seconds declination. These coordinates point to NGC 3621, a galaxy that I've actually done a lot of scientific research on. The galaxy, which is located in the constellation Hydra, is classified as a spiral galaxy. A typical spiral galaxy has a spherical bulge of stars in its center and a disk of stars that contains spiral structures. However, NGC 3621 doesn't have a bulge. It only has a disk. Moreover, the disk does not contain very sharply defined spiral arms, but instead has a series of wispy filamentary structures. Astronomers use the technical term flocculent to describe galaxies with these types of wispy structures. NGC 3621 is actually bright enough to be seen with an amateur astronomy telescope, but don't ask me how to find it. The stars in this part of the sky don't seem to form any distinct shapes, and I've never looked at it through a telescope myself. One of my references described NGC 3621 as looking like a, quote, bright oval, unquote, which sounds like what I would expect. As a professional astronomer, I have been working with this galaxy for about 18 years. A lot of my research has focused on interstellar dust, which absorbs starlight in the ultraviolet and visible parts of the electromagnetic spectrum and re-radiates the energy as infrared light. Since interstellar dust tends to be found in dense nebulae where stars are forming, a lot of the infrared radiation comes from dust absorbing the light from very young stars. However, I found that in NGC 3621 and a few other similar spiral galaxies without bulges but with wispy spiral filaments, a significant fraction of the far infrared radiation appears to come from dust absorbing starlight from old stars, although my results for NGC 3621 are not quite as clear as for other galaxies. I haven't quite figured out exactly what's happening in these galaxies, but at the moment, I think my results might have something to do with the overall structures of the individual galaxies or the amount of interstellar dust within the galaxies. As a side note, I found it a little difficult to work with NGC 3621 because a couple of nearby stars within our own galaxy fall between us and the southern half of NGC 3621. In the mid-infrared, these stars are very bright and make it difficult to actually analyze the infrared emission from the galaxy itself, so a lot of my analysis has been restricted to the northern and central parts of the galaxy. In any case, this galaxy may be much more interesting for reasons that don't necessarily involve the interstellar dust. In 2007, a group of astronomers working with infrared data from the Spitzer Space Telescope identified the presence of highly ionized neon in the center of NGC 3621. And yes, that's the same type of neon found in neon lights here on Earth. That highly ionized neon was the first hint that NGC 3621 contains a supermassive black hole. The black hole itself does not produce light, but gas falling into the center of the black hole gets highly compressed by gravity, and this makes it really hot and makes it radiate a huge amount of electromagnetic radiation. The ionized neon in the center of NGC 3621 is associated with this really hot gas. Observations with the Chandra X-ray Observatory found a point-like X-ray source at the center of NGC 3621 that could only come from the environment around a supermassive black hole, thus confirming that it was there. In some Hubble Space Telescope images previously used for completely different purposes, one of which I will describe in a couple of minutes, astronomers found a small cluster of stars orbiting the potential black hole and used that to estimate its mass, which is about 3 million times the mass of the Sun. This discovery is particularly important because it is a supermassive black hole found at the center of a galaxy that has no bulge. Typically, astronomers find supermassive black holes in the centers of galaxies with stellar bulges, and the mass of the black hole is known to be directly proportional to the mass of the bulge. This relation indicates that the growth of galaxies' bulges and the growth of galaxies' central supermassive black holes are somehow interconnected, although it's not quite clear how. However, NGC 3621 has no stellar bulge, so it does not quite fit into this relation very well. It's also not the only galaxy with a supermassive black hole, but without a bulge, although it's a really good example of one. Astronomers are still trying to figure out exactly what's going on with these specific black holes, which means that they will be spending much more time observing NGC 3621 in the future. And now for something completely different. NGC 3621 is close enough to Earth that it is possible to identify the individual stars within the galaxy. This is important for being able to measure distances to NGC 3621. In our own galaxy, we can use a geometrical technique called parallax, which I'm not going to describe in detail right now, to measure the distances to individual stars. If we know the distances to specific types of stars in our galaxy, and if we measure the apparent brightnesses of these types of stars as seen from Earth, then we can determine how much power is emitted by these stars. Astronomers use the term luminosity to refer to this total emitted power. If we see these types of stars in other galaxies and compare the apparent brightnesses of these stars to the luminosities that we expect these stars to have, we can calculate the distances to these galaxies. So, as I said, NGC 3621 is close enough that we can identify some specific types of individual stars within the galaxy. Back in 1997, the Hubble Space Telescope was used to identify stars called Cepheids within NGC 3621. A Cepheid is a variable star where the period of variation in the star's brightness is directly related to the star's luminosity, which means that a comparison of the period in the Cepheid's variation in brightness to how its average brightness looks from Earth can be used to estimate the distance to the star. A total of 69 Cepheids were initially found with the Hubble Space Telescope in NGC 3621, and the distance to the galaxy based on those stars is 21.7 million light-years. Although a lot of people have spent a lot of time reanalyzing these measurements and often get slightly different answers. Astronomers have also been able to identify both the brightest red giant stars and blue supergiant stars within NGC 3621. These types of stars are a little more tricky to identify, in part because they don't blink like Cepheids do, and it requires a little more work to figure out accurate luminosities for these stars, but they can still be used to make accurate distance measurements to other galaxies. The brightest red giant stars in NGC 3621 give a distance of 23.2 million light-years to the galaxy, while the blue supergiants give a distance of 21.3 million light-years. If we take the average of these two measurements and the one from the Cepheids, we get 22.0 million light-years, or because astronomers like to work in megaparsecs, 6.76 megaparsecs. We could probably say that the average has an accuracy of about a few percent. These measurements of highly accurate distances to other galaxies may sound like some sort of esoteric technical competition that astronomers participate in so that they can win free trips to Hawaii or South America, complete with a paid-for hotel room and 3 free meals a day. However, these types of distance measurements are extremely important scientifically for calibrating the various other techniques used to measure distances to galaxies where we can't see the individual stars, and the measurements are also important for studying the expansion of the universe. This expansion is actually seen by looking at Doppler shifting of light from other galaxies, which, including NGC 3621, almost all seem to be moving away from our own galaxy. We also know that more distant galaxies are moving away faster than nearby ones. We expect, at least for galaxies within a couple 100 million light years of Earth, that the ratio of the velocity at which the galaxy is moving from Earth to its distance should be a constant. So if we can measure the ratio for nearby galaxies like NGC 3621, we can accurately estimate the distances to more distant galaxies using measurements of their velocities. That is why all of these highly accurate distance measurements are so important. So that's why astronomers are so interested in NGC 3621. The location on the Earth's surface corresponding to the position of NGC 3621 in the sky is a place in the ocean 339 kilometers northwest of the North Island of New Zealand and 444 kilometers south-southeast of Norfolk Island, give or take a kilometer. I could have described the location as roughly halfway between these islands, but since this episode has included a lot of discussion about the importance of making accurate distance measurements, I thought that I needed to measure the distances from the islands to this point in the ocean with much more accuracy. The website for this podcast is www.randomastronomicalobject.com. You can visit the website to download episodes of the show, read information about the astronomical objects, view images of those astronomical objects, and send me random feedback. The audio was recorded and edited by George Bendo. The music is Immersion by Sasha Endy at www.sasha-endy.de, which is distributed by filmmusic.io under CC 4.0 attribution license. The sound effects are from the Freesound Project at www.freesound.org. Thanks for listening.